Hello, everyone. Thanks for joining us today. My name is Matt Willard, and I'm the Senior Marketing Manager at Fluence Analytics. Before we start the webinar, please note the chat feature at the bottom of your screens. You can use this to make comments or pose questions to our panelists during the webinar, and Dr. Reed will respond to your questions at the end. Fluence Analytics is a startup headquartered in New Orleans, Louisiana, that spun out of Tulane University in 2013. We provide industrial and laboratory monitoring solutions that produce continuous data streams. Our real-time data enables process optimization. In one industrial use case, an ACOMP customer experienced a 17% reduction in cycle times worth over $1 million per year in added capacity. Today's webinar will discuss the fundamentals of polymer characterization, including detectors and techniques used for analysis, some of which are incorporated into many of our products. Our panelist is Dr. Wayne Reed, co-founder and CSO of Fluence Analytics, and the inventor of all technologies contributing to the company's product portfolio. He is the Murchison Mallory Chair in Physics and founding director of PolyRMC at Tulane University. And at this time, I will turn the webinar over to Dr. Reed.
Well, thank you, Matt. So we're going to have a very brief introduction here to polymer characterization. And as we go into it, I have to mention that it's really a vast interdisciplinary area, lots of subfields, lots of different methods that are being used. But to kind of get a handle on it, I'll break it into two areas. The first being the intrinsic properties of the polymer molecules themselves, what's their molecular weight, their intrinsic viscosity, stiffness, composition, tacticity, and so on. And then the properties of when you start putting them together into like semi-dilute concentrated solutions, the melt, all the way to the solid state, completely different properties that we measure in terms of rheology, processability, solid state structure, crystallinity, amorphousness, and so on. So today we're going to focus on the first part, which is the polymer properties themselves. So we'll be in the dilute regime of solutions and see what we can find out about polymer properties. Just to set the stage, we know that biological polymers, well, nature beat us by several billion years on building polymers. You see the globular protein, for example, extremely intelligent molecule with enzymatic properties very specific. Another manifestation of proteins being structural strength, stability, and collagen. If we go over to energy storage that nature has confabulated over the epochs, amylose, glycogen, amylopectin store energy in polymeric form, polysugars essentially. And if you go to the king of the biological molecules, DNA, which has all the information in the genetic code, it still is a polymer, and it's amenable to characterization by the types of polymer characterization methods we discussed today. Getting back to mere humanity, we've been at this maybe a couple hundred years, even a bit less, but made our own simple little polymers. You can see how simple the polyethylene is, just a bunch of carbons and hydrogens hanging off, not even any functional properties. You go to nylon, it's a bit more complex, richer structure, and you all know the kinds of things you can do with nylon. If you go over to, say, polyacrylamide, it's just a repeat of this unit here. Again, a little more complex than polyethylene, and you can co-polymerize it with other molecules. Very valuable for water purification, metallurgy, paper making, personal care, and so on. And styrene butadiene rubber, a huge global market involving these two polymers, styrene and butadiene. Again, to a solid state with all kinds of interesting viscoelastic properties. Okay, so now if we break it back down to what is a polymer, well, the chemists have all those marvelous groups to know how to fiddle with them and produce different kinds of polymers. If you take a physicist kind of view, you just kind of strip away the chemistry and see that you have a center with a monomer, a bunch of atoms, connected to another group, whether the same or different, by a bond, and there's usually a fixed bond angle here, but then you can have rotational freedom around the bond, so as you add these links on, they can be rotating in space, so you can get lots of different ways of making conformations of this. Oftentimes you'll get what are called three rotameric states, where because of eclipsing and anti-eclipsing, the conformations kind of clip into three different lower energy states. But even then, with 3 states and you have N monomers, you get 3 to the N-2 states. So if you take something like even a very small protein with only 100 amino acids, and that's very small, there's still over 10 to the 46 states, which is a gigantic number. It's comparable with the number of known particles in the universe. So it's not really fruitful to try to ferret out all these different conformations. Instead, we like to deal with different conformational families and then average properties, which is what you usually do when you have large collections of matter. So if we look at these families, the one that we get from most of our industrial polymers, the random coil, which also can be produced by, say, denaturing a globular protein or denaturing DNA. As the name implies, it has no structure to it, goes meandering through space, and a characteristic would be the root mean square end-to-end distance, where it starts to where it ends. And when you do the statistics on that, you find that it's that end-to-end length, root mean square, is proportional to the square root of the number of units or of the molecular weight of the polymer. And if there's excluded volume, in other words, you can't walk back over yourself, then it goes to the end of the 0.6 roughly. Okay, another family then would be the globule, where you collapse into a very highly organized form, like a protein, for example, and then it's spheroidal. You'll get an m to the 1/3 dependence, so quite a different scaling of the dimension compared to the random coil. If you go rod-like, like segments of DNA or collagen, then the characteristic distance is its length itself, and that's directly proportional to the mass. If we look at then branched polymers like this, or stars, or dendrimers, or combs, they'll usually have scaling laws of their dimensions between the globule and the random coil, 1/3 to 1/2. Okay, so we're going to look at some of the characteristics of these polymers, start with their dimensions. A couple very well-known and commonly measured dimensions. First one is what's called the root mean square radius of gyration. This is actually should be a square sign here. It's the mass average mean square distance from the center of mass of a given object. So it's measured by multi-angle static light scattering. That's the practical aspect of it. And the other type of light scattering people are very familiar with is dynamic light scattering. And there what we're actually doing is measuring a diffusion coefficient, not a size directly, and then you have to use some kind of a relationship to put that diffusion coefficient into equivalent size. What's used most of the time is the equivalent sphere, Stokes-Einstein, which gives you then an equivalent hydrodynamic radius based on what you actually measure, the diffusion coefficient. So they're related together. What you get with dynamic light scattering, this hydrodynamic radius, and the root mean square radius of gyration from multi-angle light scattering. If you take the case of a sphere, what you'll measure with the dynamic light scattering is pretty much the outer radius as it moves through the liquid. So that's the RH, which is equivalent pretty much to its own radius. But RG, you can see it's smaller because you have to integrate all the mass, which is not just at the center, it's all throughout the body. If it's uniform, then that's the relationship. A very clear relationship, so you can interchange between the results from multi-angle light scattering and dynamic light scattering. If we go over to our random coil, again, a lot of our synthetically produced polymers, there's a bit more statistics in that, but still there's a relationship between the radius of gyration, again, measured with respect to the center of mass of the random coil, and the hydrodynamic radius that you measure with the dynamic light scattering. So that's dimensions and the relationship to multi-angle light scattering and dynamic. Now, intrinsic stiffness of polymers is a very interesting property. We talked about a polymer kind of meandering through space like this, but there are mechanisms that can stiffen the polymer. For example, putting in alpha helix segments, or putting in double helices, or electrostatic repulsion. There's a number of mechanisms that can do that. So if you just take a little segment of that meandering, we call it worm-like chains of the meandering worm, and you project it over here, and you put one tangent vector, that's the instantaneous direction of the path here, and then you go a distance, what's called the persistence length, and look at the instantaneous direction there, T2, and you look at the angle between the beginning and end vector. When it hits 69 degrees, that's the distance it takes to get to that difference in direction is called the persistence length. So that's the idea of the persistence length. The stiffer it is, the longer the persistence length, the longer you'll persist in a given direction before kind of wandering off. So in layman's terms, the persistence length is the distance you go before you forget what direction you're going in, loosely stated. And this will relate to what we just talked about. We mentioned the radius of gyration. So the persistence length times the contour length, that's if you take this worm and stretch it out and measure it, that's big L, contour length. Then you can relate the contour length, persistence length to the radius of gyration. Now to give some visuals on this, let's consider several different polymers, all of the same mass. So they're all 1,000,000 grams per mole, 1,000,000 grams per mole. And one is a globular protein, or might be a microgel. It'll be not stiff at all. It's all coiled up. Its persistence length will be much less than a nanometer, and there it is. That's the space it's occupying. You take something like butadiene, it's got 1 nanometer persistence length, but it's very light, not too much mass, linear mass density. Then you get something like this. It's much more stretched out than this, but a bit less than polystyrene, which has roughly the same persistence length, but has a higher mass density. So they're similar, but a little bit less than polystyrene. If you go over to hyaluronic acid, which has both electrostatic repulsion and some helical nature to it, it's up to about 10 nanometers, the persistence length. And you can see that same mass molecule occupies a lot more space than these others. And if you go up to something like xanthan, a natural polysaccharide, it's now 100 nanometer persistence length. It's way bigger than all the others. Now, there's a very useful measure of this because this will affect viscosity. And so let's talk for a moment about viscosity. Everyone's familiar with the basic notion, honey is viscous and machine oil is viscous, water is not very viscous, and so on. There's two types of flows we normally talk about. One is called Couette flow, where you have, say, a stationary plate here, and then another plate up here, and it takes a certain amount of force per area to get up to a certain velocity of that plate, just to have it moving at a speed v relative to the stationary plate here. And so then the liquid, it has a stick condition here, it has a stick condition up there, so you'll have velocities going from 0 to this big V, and that gradient then is called the shear rate, the rate of change of velocity with respect to this y coordinate. And what relates it, the bigger the viscosity, you see that's a proportionality parameter, the bigger the viscosity, the more pressure it takes to achieve that velocity, the more viscous the liquid. So another flow, and you can do this like in concentric cylinders, that's a popular Couette device. If we go into what's real workhorse in chromatography and polymer characterization is Poiseuille flow, where you have a capillary with a given radius, and now you have a pressure between here and the other side, this delta P, and then that drives the liquid, and since you have stick velocity, you have 0 velocity at both of these boundaries, you have a maximum in the beginning, and if you're low Reynolds number non-turbulent, then in Newtonian, you'll get a nice parabolic flow profile like this. And the relationship then between that pressure difference is related to the length of the capillary, this L, the flow rate at which you pump through, and 1 over R to the 4. So it's extremely sensitive to the radius of the capillary. And then there's the viscosity. So let's just a quick mention. That's normally when we have what we call Newtonian flow. So Newtonian liquid is one whose viscosity, this eta we're talking about, is independent of how fast the shear rate is, how big the shear rate is. Water is like that. But a lot of polymers, as you increase the shear rate, which would mean, for example, pumping through a capillary more quickly, higher flow rate, they'll actually start thinning out. Their viscosity will go down. And some materials will actually go the other way and have shear thickening. So that brings us into what we're talking about before, more like the overlap concentration, melts and liquid states, and you have a whole area of rheology. That's just the gateway to it. That's a vast field all of itself. We're not going to touch it today. And I just will mention, you can get some non-Newtonian behavior out of even non-interacting polymers, just because they might be big enough that they'll start to shear align with the flow. And so you can get these effects even without a lot of concentration. Okay, so we're not going to worry about being off the Newtonian plateau. We're going to be nice and Newtonian. And that's usually okay, because when you do your polymer analysis, you're usually in very dilute polymer solutions where the shear rate doesn't have that dramatic of an effect. Okay, so let's just have a mini course here in viscosity. Viscosity of the solution, again, you can relate to it, water versus honey. Honey has a lot higher viscosity than the water, and what it's composed of now is, this is A to S. That would be your pure solvent viscosity, whether it's water, oil, or honey. And as you start adding particles in, like polymers, it adds internal friction, because really viscosity can be conceived as internal fluid dynamic friction as well. As you add in a concentration C of these particles, you start increasing, usually, almost always, the viscosity of the liquid. And what determines how much it viscosifies is what's this here. This is called the intrinsic viscosity, this eta in brackets. So that's that's a single polymer fundamental property. It's very useful for understanding the architecture and other properties of the polymer. So we want to look at that a little bit more. As you start concentrating your solution, then the polymers start to interact, and you get the C-squared terms with some kind of a hydrodynamic interaction and so on. But we'll be down here dilute enough, as I said today, that we can just worry about this term here. So you can see that to measure it is actually quite simple. All you have to do is have a way of measuring a solution with or without polymers in it. So let's say we have polymers here, and we thickened up the solution a bit by putting polymer in. Then we measure the pure solvent, subtract it off, divide by the solvent viscosity and concentration. That's just a rearrangement of this equation here, having no higher terms. And you've measured now your intrinsic viscosity. That's in the limit that you go to zero concentration. So usually people do several concentration determinations, extrapolate to zero, and get this very important intrinsic viscosity. But what the intrinsic viscosity measures, you can see that this is dimensionless, viscosity times concentration, so it has inverse units of concentration. In other words, volume per mass. It's the hydrodynamic volume of the molecule per unit molecular weight. So let's go back to our visual of before, and you can see that, again, all have the same, these are the same molecules, all of 1 million molecular weight. What determines it, molecular weight here on the bottom is the same for all of them. So it's the hydrodynamic volume which determines the intrinsic viscosity, and you can see the volume is getting bigger and bigger as we go this way. This xanthan has a hugely larger intrinsic viscosity than, say, this microgel of equivalent mass. So you'll get very different viscosifying powers out of these. Okay, in terms of the actual measurements, a really inexpensive way of doing it is to just use Poisson's law that we briefly covered. You have a capillary of known length, you have a pressure transducer. That's the heart of it. It costs around between $1,000 and $2,000. And you hook that up to a capillary, have a known flow rate, and you don't need any calibration at all. That's a really nice feature of this, because you end up dividing the viscosity with the polymer by the viscosity of the solvent, so any calibration cancels out. And so you can get reduced intrinsic viscosity with no calibration. However, if you go to a bridge viscometer, it has 4 capillaries, it's much more sensitive. And so it's pretty much the standard operating viscometer for GPC because of its sensitivity. It can eliminate thermal and pressure fluctuations, high sensitivity. So it's really excellent in separations, gel permeation chromatography, SEC. Of course, it is more expensive, and you do have to calibrate it. So there's always trade-offs. If you look at some sample data, this is the exact same pulse that went first through a bridge viscometer, you can see, and then through the single capillary viscometer, one right after the other, same sample. You can see how much cleaner the bridge viscometer is compared to the single capillary. Another note on the bridge, you can't use it in continuous systems. It's meant to work on pulses coming out from GPC. If you use it on a continuous system, it will eventually zero itself out and you'll lose your signal. So when we're doing online work, we go to the single capillary. Okay, so now another property here is a molecular weight distribution. Probably they meant weight. So the actual distribution, when you start with a biological molecule like a protein, it has a unique molecular weight due to its primary sequence of amino acids, and barring mutations, you always get the same molecular weight out. Now, when you produce polymers synthetically, you always get distribution. Even when you use living techniques and so on, you still get distribution. And so there's a large part of polymer characterization devoted to finding those distributions, and the gold standard is pretty much size exclusion chromatography / gel permeation chromatography, which then gives you these actual distributions. Now, besides being kind of a neat looking curve, you can't do much in terms of numbers until you take averages of it. So when we get distribution, we take averages. You have a number average, which you're most familiar with. You take, for example, say these were exams. You would take the number of students who have the grade M sub I, and I times M, sum all those up, and then divide by the sum of the number of students in the class, and that would give you your average grade. So that's a typical number average, and you can get that, and you can see it works on the lower part of the distribution. But a more useful average is the weight average, and that doesn't make much sense when you grade a test, because you don't usually take a student's the number of students and multiply times the grade squared. That would give more weight to the higher grade, so you end up with a higher weight average grade than if you just take the number average. And in fact, that's what you can see. The weight average here is higher than the number average, and you can get up to even higher averages. You could take the number of a grade times that grade cubed and get what's called the Z average, which is even higher up. And so that progressively weights the distribution toward higher and higher masses. There are techniques which measure N, for example, osmometry for number average molecular weight, W, which is from light scattering. And frequently this weight average is the single most important average determining a lot of properties, including brittleness and processability and other properties. Z average sometimes you can't avoid, because that's what you'll get. For example, a DLS measurement gives you a Z average diffusion coefficient. You can't get away from that. The multi-angle light scattering will give you a Z average radius of gyration, but it does give you a weight average molecular weight. Okay, so I mentioned light scattering, and just to go over that very briefly, it's a very simple method in principle. Nowadays we use lasers. We usually have them vertically linearly polarized, which means the electric field is coming out of the slide at you. And then the maximum scattering occurs in the plane of the slide. So we usually put our detector in the plane called the scattering plane. So we have a detector here, and you can see where the cross-section of the laser beam with the field of view of the detector, that little cross-hatched area there, that's what's called the scattering volume. And that's typically very small, like say nanoliters, whereas your whole sample might be a milliliter. So it's way, way smaller than the volume of your actual sample. The scattering angle is reckoned with respect to the throughput going in the direction of the laser would be 0. As you swing out, you grow an angle. 90 degrees would be here, and then you get a scattering vector amplitude, which we need not go into, but it's common to all scattering measurements. And then we have our detector, which again is in the plane, and you send the signals off to your computer. DLS requires fast sampling, at least a microsecond. So you usually use a photomultiplier or avalanche photodiode. And again, you get a diffusion coefficient, whereas static light scattering, we're concerned with the total intensity scattered. So it's not important to measure quickly. You can even have something as slow as 1 second. You can use a CCD, which normally is milliseconds to seconds. You can throw in a photodiode, no problem. But you get weight average molecular weight with the multi-angle to get the radius of gyration, and you can get virial coefficients. I'm not going to go any further into that, but I do want to mention just briefly ranges of scattering, because this is actually very important. You have a wavelength of your laser. For example, in Fluence's Argin unit, it's 660 nanometers, very typical. Now, if you take something like a typical globular protein, that's 10 nanometers, you can see it's way smaller than the wavelength of light, and that's termed a Rayleigh scatterer. And in this scattering plane, it will scatter equally in all directions, which means you can measure at any angle at all. And it's convenient when there's 90 degrees, and you've got all the information you get. There's no virtue at all in measuring multiple angles when the dimension of the scatter is a lot smaller than the wavelength of light. However, when it does start to grow, something gets, for example, on say the order of 100 nanometers, 200 nanometers, then you no longer have this nice equal distribution at all angles. It starts to get peaked in the forward direction, and that's when you need multi-angle measurements. because you have to extrapolate the zero angle. And then as either you get very large or you get into colloids, which tend to be more solid, you get into what's called me-scattering, which is very complex, and you can see the pattern can be all kinds of things and have minima and maxima, and that's usually not part of typical polymers, which are say a couple million and down. But for colloids on hundreds of nanometers on up, it's very important. Okay, so I mentioned before that GPC is the gold standard. I'm sure a lot of you're not only familiar with this, but practice it, so I'll be brief. Basically, you have an HPLC pump, you have an injection loop where you put in a little pulse of sample anywhere from, say, 10 microliters up to 100 microliters. You go through the GPC column, which spreads that out. If it's really according to size exclusion chromatography, SEC, then it'll separate according to hydrodynamic volume, which we already mentioned in conjunction with intrinsic viscosity. It doesn't separate according to mass. That, of course, is a misnomer. So you have a stream coming out that's separated, then you can go through whatever detectors you want. We already mentioned some of the virtues of multi-angle light scattering. If you have particles, say, many tens or hundreds of nanometers, viscometer, you get that intrinsic viscosity, important architectural feature of your polymers. Refractive index or UV, they both measure concentration. So a complete multi-angle chromatogram might look something like this, where you have, here's the molecular weight distribution, which we already discussed. This is a pretty broad one. And we have the radius of gyration in blue with this exponent, thanks to our multi-angle light scattering, and then the viscosity Markov relationship with its own exponent, thanks to the viscometer. Okay, so if you look at the GPC column itself, just to drill down a little bit, there's usually particles in there, and they're porous particles, and they have very complex surface features. And you can see what happens when you inject in an unseparated mixture of big particles and little particles. The big particles kind of just go barreling through. They're too big to get trapped up in these all these nooks and crannies, whereas the little ones actually entropically explore. They go in and out and go through these serpentine paths, and so it takes them longer to come out. So the general rule is big comes out first, small comes out later. Okay, when you have multi-angle multi-detectors, it's interesting to see when you get your chromatograms that they do not overlap at all. And it's not that because of dead volume, these have been corrected for interdetector dead volume, and it's not any mistake. It's the fact that the RI detector is actually measuring concentration, so you get a peak over here. Light scattering is measuring concentration times mass. And remember, bigger mass is earlier, so concentration times mass pushes the peak this way, and the viscometer is measuring something like concentration times mass square root or something, so it's in between. Okay, I just want to give two quick examples of use of, say, multi-detector in characterizing polymers. This was a case study, just briefly, where we had oligosaccharides, which are sweet, very small oligosaccharides with gelatin. And these are confected together to make gummy bears and other sweet confections. The problem with the manufacturers is that a lot of times they would spontaneously separate the gelatin and the oligosaccharide. And so we were tasked to find out what is the polymer molecular basis for that. And it seemed like the gelatin would be the bad guy because it's a complex protein. It's extracted from animal hides with acids and bases and so on. And oligosaccharide is just a polysaccharide that's been broken down either enzymatically or by acid or base. But it turned out it, in fact, is the oligosaccharide. When you look at the oligosaccharide GPC, if you just look at the RI, you see a main peak. You see a little hump here, which you'd probably be inclined to ignore. But when you have the light scattering coupled, which is this here, it's a very big signal, meaning it's a small population, the concentration, but they're big. And when you go into the thermodynamics of compatibility, it's a small amount of big polymers can lead to that phase separation. The practical upshot is it allows the manufacturer a means of screening, say, tons of oligosaccharide before buying it to make sure that the supplier has done the work of breaking it down enough that they don't have this residual long chain population, which can be utterly disastrous. And then one other quick case study. This is gum arabic, same issue. Confectioner wants to use this to viscosify a liquid, and because it also has some protein component, it can emulsify aromatics like flavors and fragrances. Question is, when you buy this from Northern Africa, tons of it, how do we know we're getting the good stuff that will viscosify and emulsify? So when you do the GPC on this, you get a more complex set of signals. You can see the RI. The main part of it is over here. Remember, small is later. So most of it is in this RI peak over here, small stuff. And then you get a little intermediate and you get this little hump over here. But if you look at the light scattering, well, yeah, you get a lot where most of the mass is, but you get a very big signal over here where there's only a little mass, kind of reminiscent of that last slide we saw. And then the viscometers in between. The short of it is when you analyze this, now we're doing versus molecular weight, you see that most of the material, that's the vast amount of concentration, is low molecular weight stuff. Doesn't do anything for you. Doesn't viscosify, doesn't emulsify fragrances and flavors. That's all left to, if you look over here, you can see viscosity, our intrinsic viscosity, what we were talking about, shoots up at these very high masses. That's where you're getting the viscosity power out of this little part of the mass distribution. And then you can see Rg taking a big dip here, and viscosity is way down by then. That's where the proteins have complex with the polysaccharides, giving you the emulsifying power. So anyway, this lets you assess, how much is just kind of like chaff or excipient, how much is in emulsification, and how much is in viscosification. Okay, in terms of branching, that's a very complex field in itself. I don't really want to say much about this, except that with GPC, as you branch something, for the same hydrodynamic volume, you'll get a bigger mass. So if you take a hydrodynamic volume, remember that's how your column is separating, so you have an unbranched molecule here, and you go to a branch one, in that same volume you have a lot more mass, so it comes out the same place, but it's a much greater mass. So that's dipping your toe in the water of the vast complex field of branching. I don't want to dwell on that. Instead, I'm going to move on to monitoring. First, I want to say what we're talking about up until here with the chromatography was size exclusion chromatography, where the polymers do not interact with the column. The other extreme is called interaction chromatography, where they deliberately do interact, like HPLC, or in case of polymers, there's several methods. For example, temperature rising elution fractionation, where you actually precipitate out your polymers on the column and then you heat it up, and then according to molecular weight and composition, they start desorbing from the column and going through your detectors. Then there's hydrophobic interaction and hydrophilic interaction. Again, these are all fields unto themselves. And just as a parting shot from fractionation, field flow fractionation has had a long, painful history, but it's starting to emerge as a useful technique where you have no column at all, no packing material. You have your unfractionated material, you pump it through your channel, and then you have some kind of a field. And the simplest field is a cross flow of liquid, which will then separate you out again, big to small. In this case, the small comes out first and the big later. But that's no column packings, no kind of voodoo mystery inside the column. You can use electric field and gravity. So anyway, this has been developing for a long time. It's becoming more practical. Okay, with that said, I wanted to spend the rest of the webinar talking about continuous monitoring. And I'll start off with something that doesn't involve any time dependence. We call it automatic continuous mixing. What we do is take a quaternary pump, which is able then to take 4 different liquids and mix them in any fraction desired, or any ramp, continuous ramp desired, in a mixing chamber, and then you can put it through detector train, any detectors you want. You can see we like static and dynamic light scattering, we like viscosity, we like UV and RI detectors. So as a quick example of that, let's look at a polyelectrolyte. That's a electrically charged polymer. So here it is flexible, but it has negative charges on it. For example, hyaluronic acid in connective tissues. And so it tends to stretch out because the charges repel each other. But if you put salt in, it starts to crumple up because the charges are screened. And so now you know that intrinsic viscosity measures the volume per mass. We haven't changed the mass by putting salt in, but we've shrunk the volume, so the viscosity should go down. So now we take our automatic continuous mixing, and we have a constant concentration of this hyaluronic acid, and we add salt, and we go from 0 on up, and you can see indeed the viscosity comes tumbling down quite dramatically as the molecule shrinks and the intrinsic viscosity goes down. Same token, the light scattering goes up. I won't get into that effect, but it complements viscosity effect. Okay, and then just one other example of the automatic continuous mixing. Here we have a neutral polymer, polyvinyl pyrrolidone, no charge on it at all. We start putting in sodium dodecyl sulfite micelles, they're negatively charged micelles, molecular weight, several thousand, 5, 10,000, whatever. And it turns out they actually associate with the polymer. They kind of decorate it and turn it into a pseudo polyelectrolyte as if it were being charged. So when we first saw this, it was rather remarkable because here we are putting in micelles at fixed polymer concentration. Look what happens to the scattering intensity. It goes down. You would think it would go up because you're adding more scatters, but it goes down. And by the same token, the viscosity is going up. And so the reason for both is as you start decorating the polymer with negative charge, it expands out. The viscosity goes up. You can see that here, and then the interactions get stronger, and that pushes the light scattering down. Again, complementary effects. Okay, so that's the last that I'm going to say about steady state and continuous monitoring. What happens when things are happening in the solution, like you have aggregation going on, or you're degrading a polymer, you're separating a phase, or you're actually polymerizing, or any number of other processes that happen in time. We're in a kinetic domain at that point. Let's see how we can use the techniques kinetically to get information that you can't by using our equilibrium techniques like GPC. So for example, if we take a dry polymer, this is polyacrylamide, we dry it, now we throw away our GPC column and we just recirculate material that's dissolving through a refractometer. It's that simple. You can see that it gradually goes in the solution. This is a refractometer showing the concentration. In about 3 hours or so, it's pretty much in solution. Now, if you take that same material, how it's produced, say in an inverse emulsion, it's in a liquid phase in an emulsion, and you dilute it with a surfactant in aqueous phase. You break the emulsions, you release the polymer, and you can see that it solubilizes in a matter of a minute or two. And so that's the advantage of going liquid to liquid without any drying step. And in fact, when we do our automatic continuous online monitoring and polymerization reactions, we cut out any drying step. We go strictly from liquid to liquid, and we choose the liquids we want to go into, and we have very fast dissolution into the new liquid, and we're ready nearly immediately to make measurements. Here's an example of aggregation. This is a monoclonal antibody. And what we're measuring here is the molecular weight of the aggregates and all the proteins divided by the native protein. So if it's 1, that means there's no aggregation. And we did this using the RGen. It's a multi-sample light scattering unit from Fluence. You can do 16 samples at a time, control temperature and such. And we ran this out 6 days. 30 degrees, nothing happened. 45, you can see it's starting to go. And then it very quickly goes up as you raise the temperature. And this is a logarithmic scale, so the effect is very dramatic in terms of the aggregation rates. So here you're seeing in real time the actual aggregation process. This is a whole field unto itself. I'm not going to say anything more about it right now. Instead, to close, I wanted to go over a few slides with what I mentioned, automatic continuous online monitoring of polymerization reactions, or ACOMP. And we started this nearly 20 years ago. In fact, it is now 20 years, and our motivation was to get fundamental insight into kinetics and mechanisms of polymerization reactions, working with our good friends, the synthetic polymer chemists. Well, that quickly morphed into doing optimization reactions at the bench level, pilot level, and then the big brass ring, always from the start, was, can we go to full-scale feedback control of industrial reactors? If we can do that, we can save energy, we can save non-renewable resources, make more efficient use of plant time, of labor time. We can have higher safety standards. You don't have workers going in and sampling dangerous reactors. We'll be producing less emissions per kilogram of product. It's win-win all the way around. We have better products, higher consistency, and we can even produce products that we can't do now without control. So that has been a dream, and actually, as Matt said at the beginning, Fluence spun out of Tulane about 5 years ago, with this as one of its main missions, to do full-scale industrial reaction monitoring and control. So here's the idea. Usually when you think of monitoring, you think of putting probes right in the reactor. But in a polymer reactor, you get inhomogeneous, you get turbid, you get viscous. It can be a bad place to be, so we don't want to fight that battle, especially with optical type probes. So what we do is instead of going in there, is we pull out a continuous stream, very small, maybe a few milliliters an hour, and we can dilute it any way we want. We can condition it any way we want. We can invert phases, we can filter, we can volatilize off monomers and so on. And so what we basically have is a continuous stream, analytical grade stream of dilute polymer solution where we can, harking back to the beginning, measure the polymer characteristics. You can put any detectors in you want. We, again, like light scattering and viscometry, UV, vis, absorption, refractive index, but we'll put in conductivity, polarimeters, pH, FTIR, NMR, and so on. This is an example of what a unit looks like from Fluence, where you have the complete lab set up and all the instrumentation side doing what you see here. Now, it's not a chromatographic technique. There's no columns here. Okay, so it's unfractionated, so you don't have all the stability problems and other headaches at GPC. Don't get me wrong, we like GPC, but we don't like to put it in factories at this time. This is a much more robust phase. You don't have wandering baselines. You have a continuous feed of this analytical grade solution. Now, that being said, you can always put in at the end of the line a GPC unit, and sometimes we'll do this for niche applications because the concentration we're putting through our detectors here is the same concentration you would normally inject into a GPC unit. So at times we will add the GPC on, give another dimension of analysis. Here's an example of monitoring copolymers with the ACOMP. We're measuring both the instantaneous composition. This is butyl acrylate and methyl methacrylate. This is the instantaneous amount of butyl acrylate at any time during the full 100% conversion from monomer to copolymer. And you can see it's drifting upward. So the chains as we go along get richer and richer in butyl acrylate, and that's because methyl methacrylate has a much higher reactivity ratio than butyl acrylate, so it eats itself up more quickly, leaving more butyl acrylate, so it's getting richer in butyl acrylate. So we're measuring that. At the same time, we're measuring the weight average molecular weight. You can see that coming down, very classical for a free radical reaction, and the intrinsic viscosity. So we have the package of characteristics being measured in real time. Now, it was always tantalizing from the beginning that, like, if we can monitor, we should be able to control. It took us a while to get there, but we finally have gotten there. And the basic idea is you have a reactor, whether it's batch or semi-batch or continuous, and there's different knobs you can turn. You know, you can purge out nitrogen to get a free radical reaction going. You can use oxygen to slow it down. You can add co-monomers, chain transfer initiator, change temperature, and so on. Now, the ACOMP system, as you know, is measuring all the polymerization characteristics as they're happening, including as you turn these knobs. So the idea is to take those characteristics, build a controller, feed it back, and turn the knobs to get the polymer you want. So here's an example of a polymer characteristic, just a conversion, to be simple. And this conversion versus time of a simple acrylamide free radical reaction, this black path was made by raising the temperature incrementally, and that speeds it up. And then we backed off, and we did this manually. We had an engineer, and we said, Natalie, keep the temperature constant, 45. Now feed in initiator, just like a computer game. Follow that path just by feeding an initiator, because that will speed up the reaction just like temperature does. And you can see she did quite well. She stayed within a few percent of the trajectory. Now this is just a warm up to where we're going. From there, we say, let's do something really interesting like the molecular weight. So if you look at the molecular weight, weight average molecular weight is a function of time in an uncontrolled batch trajectory. The normal tendency is it'll come down. That's well known. And so we said, look, we have control now. Let's do something against the natural tendency. Let's have it go up. And in fact, let's see this red line. Let's put a positive, straight red line there and try to follow it. And the controller we built, you can see, did quite well. It was with better than 1% average error all the way. So we did control of the molecular weight. And they said, what about composition in a copolymer? So we took styrene sulfonate and acrylamide. This is the instantaneous fraction of styrene sulfonate. If you just let it go uncontrolled in a batch, styrene sulfonate has a much smaller reactivity ratio than acrylamide. So acrylamide eats itself up, leaving the styrene. Sorry, no, styrene sulfonate goes quickly, so its fraction goes down, and you would then end up actually making homopolymer at the end. So our target then was to keep the styrene sulfonate the same. That's the horizontal gray line. You can see the controller did pretty well in terms of keeping it constant. So that gives us, you're no longer a victim of reactivity ratios that nature gives you. You can work to control the composition you want. You can see the pumps, meanwhile, are automatically doing this in order to give us that. It's not obvious where you have to be and what you do, but it's all being automatically taken care of. Okay, so to summarize, today we're looking at this vast field of polymer characterization and just looking at only individual polymer molecule characterization. We were emphasizing dimensions by radius of gyration, static light scattering, multi-angle, hydrodynamic dimensions with dynamic light scattering, molecular weight distribution, stiffness to persistence length concept, intrinsic viscosity. And then we emphasized light scattering and viscometry and how when you connect this to gel permeation chromatography for non-reacting systems, non-evolving systems, you get a very complete chromatographic overview of your system. And then we briefly introduced some of the advantages you can get when you use continuous methods, especially when things are happening, like polymerization or aggregation, and the new power it gives you to both monitor, for example, protein aggregation, or monitor and control, like we said with polymerization reactions, where by monitoring them, we can also turn control knobs and seek to get the right polymer every time, and the other advantages we already discussed. And that's where I'll end. Thank you very much.
Thank you, Professor Reed. At this time, we'll go through some of the questions. So if you have any other questions, please submit them through the Q&A or chat features at the bottom of your screen. The first question is in relation to Rayleigh scattering. Why is 90 degrees a convenient angle for scattering?
So the main reason is usually you get the least amount of stray light at 90 degrees. And stray light is the biggest single problem in light scattering. It always has been historically, because you're detecting the same wavelength that you're incident with. So you can't use optical filters to get rid of stray light. You can't chop the signal. You just have to minimize the stray light or somehow take account of it. So 90 degrees is best for that. And second, if you happen to be using a square cell, then it's the natural angle geometry.
Thank you. The next question, is the order of detectors after the columns important?
Oh, you got me there. No, it really depends on the dead volume of each detector plus its sensitivity to back pressure. For example, refractometers are often very sensitive to the slightest amount of back pressure. So oftentimes you put that at the end, because if it gets back pressure, it can crack a very expensive cell. So we'll typically put that at the end. That being said, all else being equal, we would put it in order, the lowest dead volume first, followed by the next highest dead volume, and go down the line that way.
Thank you. The next question, how often are RI and light scattering different in industry? Besides the case studies shown, is this common?
Wait, how they're different? I'm actually not sure what they mean by how are RI and light scattering different.
Show them which slides.
In relation to slides 18 through 20. I'm not gonna have time to go through that.
I mean, if it's how they're, so we mentioned that the RI measures concentration, and the light scattering measures molecular weight. So in that sense, they're very different. The RI is just going to give you concentration. The light scattering will give you an absolute molecular weight. It does require that concentration measurement, however, so if you have light scattering, you have to also have a concentration detector, whether RI or UV. I think that probably answers it. Okay.
Okay. Thank you, Professor Reed. We don't have any more questions at this time, so we're going to wrap up the webinar. I'd like to thank all of you for attending today. By early next week, I'll send out a recording of the webinar as well as a PDF of the webinar slides. And if you would like to discuss potential applications, engineering projects, or if you have interest in any of the Fluence Analytics products, ACOMP or Argin, please reach out to us. My name is Matt Willard. and I'll be the one following up with you all directly. So again, thanks again, and we'll talk to you soon.